Question 1. Analysis of a proposed LED lighting upgrade for a manufacturing facility, which promises significant energy savings, raises concerns for the certified energy manager regarding the electrical safety implications of integrating the new system with the existing power infrastructure. The vendor has provided documentation stating the new fixtures meet relevant safety standards. What is the most appropriate course of action for the CEM to ensure compliance with U.S. electrical safety regulations and best practices? Option A. Prioritize the energy savings and payback period of the LED upgrade, proceeding with installation as quickly as possible to realize financial benefits. Option B. Approve the upgrade based on the vendor's assurance of compliance and the projected energy savings, assuming the existing electrical system can handle the new load. Option C. Conduct a thorough review of the proposed LED lighting system's electrical specifications against the National Electrical Code, NEC, and relevant OSHA standards, and engage a qualified electrical engineer to assess potential impacts on the existing infrastructure and perform a risk assessment. Option D. Rely on the facility's maintenance team to identify any potential electrical issues during the installation process. Correct answer is C. Conduct a thorough review of the proposed LED lighting system's electrical specifications against the National Electrical Code, NEC, and relevant OSHA standards, and engage a qualified electrical engineer to assess potential impacts on the existing infrastructure and perform a risk assessment. Explanation. Scenario analysis. This scenario presents a common challenge for certified energy managers, CEM, where a proposed upgrade, while offering potential energy savings, introduces new electrical safety considerations. The challenge lies in balancing the drive for energy efficiency with the paramount responsibility of ensuring the safety of personnel and the facility. A CEM must not only understand the technical aspects of energy systems, but also the regulatory framework governing electrical safety. This requires a proactive approach to risk assessment and a thorough understanding of applicable standards, rather than a reactive one. Correct approach analysis. The correct approach involves a comprehensive review of the proposed lighting system upgrade against relevant electrical safety standards and practices, specifically those mandated by U.S. regulations for workplace safety. This aligns with the CEM's ethical and professional obligation to prioritize safety. It necessitates consulting the National Electrical Code, NEC, and any applicable Occupational Safety and Health Administration, OSHA, standards. The process should include a risk assessment to identify potential hazards associated with the new equipment, such as improper grounding, inadequate insulation, or potential for arc flash. Engaging qualified electrical professionals for design review and installation oversight is crucial. This approach ensures compliance with legal requirements and best practices, minimizing the risk of accidents, injuries, and potential litigation. Correct approach is analysis. Proceeding with the upgrade solely based on the vendor's assurance of compliance without independent verification is a significant regulatory and ethical failure. It demonstrates a lack of due diligence and a disregard for the CEM's responsibility to ensure safety. This approach could lead to non-compliance with NEC and OSHA regulations, potentially resulting in citations, fines, and most importantly, severe safety hazards. Focusing only on the projected energy savings and payback period, while important for an energy manager, is an unacceptable prioritization when electrical safety is a concern. This approach neglects the fundamental duty to protect human life and property, violating ethical principles and potentially leading to catastrophic failures that far outweigh any financial savings. It ignores the legal mandate to adhere to safety standards. Assuming that existing electrical infrastructure is adequate without a specific assessment for the new system is another critical failure. Electrical systems have load capacities and fault current considerations that must be reevaluated when new equipment is introduced. This assumption can lead to overloaded circuits, equipment damage, fires, and electrical shocks, all of which are direct violations of safety regulations. Professional reasoning. When faced with a proposed energy efficiency project that impacts electrical systems, a CEM should adopt a systematic decision-making process. First, identify all stakeholders and their concerns, including facility management, maintenance staff, and potentially occupants. Second, thoroughly research and understand all applicable U.S. electrical safety regulations, including the NEC and OSHA standards relevant to the specific type of equipment and facility. Third, conduct a preliminary risk assessment to identify potential hazards. Fourth, consult with qualified electrical engineers or contractors to review the proposed design and installation plan, ensuring it meets all safety requirements. Fifth, prioritize safety over immediate cost savings or energy efficiency gains if there is any doubt about the safety of the proposed solution. Document all assessments, consultations, and decisions meticulously. Question 2. The control framework reveals that a manufacturing facility is experiencing significant steam losses, impacting operational costs and energy efficiency targets. The facility manager proposes immediate, broad-scale replacement of all steam traps, citing their age as the primary concern. However, a review of recent maintenance logs indicates inconsistent records regarding insulation condition and no formal assessment of the existing condensate recovery system's efficiency. What is the most professionally sound and effective approach to address these steam losses? Option A. Prioritize adding new layers of insulation to all steam piping and equipment, as improved thermal resistance is the most direct way to reduce heat loss and consequently steam consumption. Option B. Conduct a comprehensive diagnostic assessment of the steam system, including detailed testing of all steam traps, evaluation of insulation integrity, and an analysis of condensate recovery system performance, to identify specific failure points and prioritize corrective actions. Option C. Immediately replace all steam traps across the facility, as their age is a clear indicator of potential failure and inefficiency, and then address insulation and condensate recovery if budget allows. Option D. Focus solely on upgrading the condensate recovery system to capture more steam, assuming that any losses from traps or insulation are unavoidable and will be offset by improved recovery. The correct answer is B. Conduct a comprehensive diagnostic assessment of the steam system, including detailed testing of all steam traps, evaluation of insulation integrity, and an analysis of condensate recovery system performance, to identify specific failure points and prioritize corrective actions. Explanation. This scenario presents a common challenge in energy management, balancing immediate cost savings with long-term operational efficiency and regulatory compliance. The professional challenge lies in identifying the root cause of steam loss and selecting the most effective, sustainable solution rather than a superficial fix. A certified energy manager must consider not only the direct impact on energy consumption, but also the implications for equipment longevity, safety, and adherence to relevant energy efficiency standards. The correct approach represents best professional practice because it prioritizes a systematic, data-driven investigation. Identifying and addressing the specific failure modes of steam traps, assessing insulation integrity, and evaluating condensate recovery potential are fundamental steps in optimizing steam system performance. This aligns with the principles of responsible energy management, which emphasize thorough analysis and evidence-based decision-making to achieve sustainable energy reductions and operational improvements. Furthermore, such a comprehensive approach is implicitly supported by regulatory frameworks that encourage or mandate energy efficiency and responsible resource management, even if not explicitly detailing every diagnostic step. An incorrect approach that focuses solely on replacing all steam traps without diagnosis is professionally unacceptable. This is because it represents a shotgun approach, potentially wasting resources on functional traps and failing to address other significant sources of steam loss, such as deteriorated insulation or inefficient condensate return. This can lead to unnecessary capital expenditure and may not achieve the desired energy savings, thus failing to meet the professional obligation of efficient resource allocation. Another incorrect approach, focusing only on adding more insulation without assessing existing trap performance or condensate recovery, is also flawed. While insulation is critical, it cannot compensate for significant steam losses due to malfunctioning traps or the inability to effectively utilize recovered condensate. This approach neglects a holistic view of the steam system and may lead to suboptimal results, failing to meet the professional standard of comprehensive system analysis. A third incorrect approach, prioritizing condensate recovery without first ensuring the steam system is operating efficiently, i.e., functioning traps and adequate insulation, is also problematic. While condensate recovery is a valuable optimization strategy, its effectiveness is diminished if the steam being generated is being lost through other inefficiencies. This approach prioritizes a downstream solution without addressing upstream problems, leading to potentially wasted investment and incomplete problem resolution. The professional decision-making process for similar situations should involve a phased approach. 1. Understand the system and its current performance. 2. Conduct a thorough diagnostic assessment to identify all sources of inefficiency. 3. Prioritize interventions based on potential impact, cost-effectiveness, and feasibility. 4. Implement solutions systematically. 5. Monitor and verify performance to ensure sustained improvements. This structured methodology ensures that energy management efforts are targeted, efficient, and aligned with professional and regulatory expectations for responsible energy stewardship. Question 3. The performance metrics show a significant increase in energy consumption across the manufacturing sector, despite the implementation of several energy-saving projects over the past year. As a certified energy manager, which approach to developing and using energy performance indicators, NPI, would best facilitate an accurate assessment of the effectiveness of these projects and guide future energy management strategies. Option A. Implement NPIs based on the percentage reduction in energy costs, irrespective of changes in energy prices or operational output. Option B. Develop NPIs that normalize energy consumption by key operational drivers such as production volume and weather data, and establish a clear baseline period for comparison. Option C. Focus solely on the total energy consumed per facility, without considering any external or operational variables. To simplify reporting, Option D. Utilize NPIs that are broadly defined and can be applied across all types of facilities within the organization, prioritizing ease of implementation over specificity. The correct answer is B. Develop NPIs that normalize energy consumption by key operational drivers such as production volume and weather data, and establish a clear baseline period for comparison. Explanation: the performance metrics show a complex energy consumption pattern across several facilities. Developing and utilizing effective energy performance indicators, NPI, is crucial for accurately tracking energy performance and identifying areas for improvement. This scenario is professionally challenging because it requires not only understanding the technical aspects of energy management, but also the strategic application of NPIs to drive meaningful change within the organization, ensuring compliance with relevant energy management standards and potentially regulatory requirements for reporting. The correct approach represents best professional practice because it focuses on developing NPIs that are specific, measurable, achievable, relevant, and time-bound, SMART, and that account for significant influencing factors. This ensures that the NPIs provide a true reflection of energy performance improvements or degradations, enabling informed decision-making. By selecting relevant influencing factors and establishing a baseline, the organization can accurately assess the impact of energy-saving initiatives, demonstrating accountability and driving continuous improvement, which aligns with the principles of robust energy management systems. An incorrect approach that fails to account for significant influencing factors, such as weather or production levels, would lead to misleading performance assessments. This is a regulatory and ethical failure because it can result in misallocation of resources, inaccurate reporting of energy savings, and a lack of demonstrable progress towards energy reduction targets. Undermines the credibility of the energy management program and can lead to non-compliance with any mandated energy performance reporting frameworks. Another incorrect approach that uses overly simplistic or generic NPIs without proper validation or stakeholder buy-in would also be professionally unacceptable. This represents a failure to adhere to best practices in energy management, potentially leading to ineffective strategies and wasted investment. Ethically, it fails to provide an accurate and transparent representation of energy performance to stakeholders, including management and potentially regulatory bodies. The professional decision-making process for similar situations should involve a thorough understanding of the organization's operations, energy consumption drivers, and strategic goals. It requires engaging with relevant stakeholders to define what constitutes performance and to identify key influencing factors. A systematic approach to data collection, analysis, and validation of NPIs is essential. Professionals must prioritize NPIs that offer actionable insights and can be reliably tracked over time, ensuring that the chosen metrics are both technically sound and strategically valuable for driving energy efficiency improvements and meeting organizational objectives. Question 4. Research into the implementation of energy efficiency measures within a large manufacturing facility has revealed a common tendency to address only the most visible or easily rectifiable energy waste issues, such as minor leaks in compressed air lines or the replacement of a few inefficient light bulbs. This approach, while offering immediate, albeit small, improvements, often overlooks deeper, systemic inefficiencies within core industrial processes like steam generation and distribution, or the overall energy demands of complex machinery. What is the most professionally sound approach for a certified energy manager to advocate for, given the goal of achieving significant and sustainable energy reductions in such a scenario? Option A. Focus on implementing minor equipment upgrades and addressing readily apparent issues as they arise, as this approach minimizes disruption to production and requires less upfront investment. Option B. Advocate for a comprehensive process energy audit that systematically analyzes the energy consumption of specific industrial processes, including compressed air systems, steam systems, and other relevant energy-intensive operations, to identify and prioritize the most impactful energy conservation measures. Option C. Implement only those energy efficiency measures that can be completed within a short time frame and demonstrate immediate quantifiable savings to build confidence with management. Option D. Prioritize the implementation of energy-saving equipment recommended by vendors, as they possess specialized knowledge of their products and their potential energy-saving capabilities. The correct answer is B. Advocate for a comprehensive process energy audit that systematically analyzes the energy consumption of specific industrial processes, including compressed air systems, steam systems, and other relevant energy-intensive operations, to identify and prioritize the most impactful energy conservation measures. Explanation: Scenario analysis. This scenario presents a common implementation challenge in industrial energy management, balancing the immediate need for operational efficiency with the long-term strategic benefits of comprehensive energy audits. The pressure to maintain production output and avoid disruption can lead to a focus on quick fixes rather than a thorough understanding of underlying energy consumption patterns. This is professionally challenging because it requires the certified energy manager, SEM, to advocate for a more resource-intensive, yet ultimately more beneficial, approach against potential resistance from stakeholders prioritizing short-term gains. The CEM must demonstrate the value proposition of a detailed audit, aligning it with regulatory compliance and long-term cost savings. Correct approach analysis. The correct approach involves conducting a detailed process energy audit that systematically analyzes the energy consumption of specific industrial processes, including compressed air systems, steam systems, and other relevant energy-intensive operations. This aligns with best professional practice as outlined by recognized energy management standards and guidelines, which emphasize a holistic and data-driven approach to identifying energy-saving opportunities. Such an audit provides a granular understanding of where energy is being used, the efficiency of each component, and potential areas for improvement. This detailed analysis is crucial for developing targeted and effective energy conservation measures, ECOM, that yield significant, sustainable reductions in energy consumption and operational costs. Furthermore, a comprehensive audit provides the necessary data to justify investments in energy efficiency projects and to track progress towards energy reduction goals, which may be mandated or incentivized by regulatory bodies. Incorrect approaches analysis. Focusing solely on readily apparent issues like fixing obvious leaks in compressed air systems without a broader audit fails to address systemic inefficiencies. This approach is professionally unacceptable because it is reactive rather than proactive, likely missing larger energy waste sources and failing to optimize overall system performance. It may also lead to a false sense of accomplishment, while significant energy savings remain untapped. Implementing only minor equipment upgrades without a thorough understanding of the process energy balance is also professionally flawed. This approach risks investing in solutions that are not aligned with the primary drivers of energy consumption, or may even create new inefficiencies elsewhere in the system. It bypasses the critical step of identifying the most impactful opportunities for improvement, potentially leading to wasted capital and suboptimal energy savings. Relying exclusively on vendor recommendations for energy-saving equipment without independent verification and a comprehensive audit is a significant ethical and professional failure. Vendors may prioritize selling their products over providing the most cost-effective and appropriate solutions for the specific industrial context. This approach can lead to misallocated resources, ineffective ECMs, and a failure to meet energy management objectives, potentially violating professional duties to act in the best interest of the client or employer. Professional reasoning. When faced with implementation challenges in process energy audits, a certified energy manager should employ a decision-making process that prioritizes a systematic, data-driven, and holistic approach. This involves 1. Understanding the specific regulatory requirements and industry best practices relevant to process energy management. 2. Clearly communicating the long-term benefits of a comprehensive audit, including potential cost savings, operational improvements, and compliance assurance to stakeholders. 3. Prioritizing audit activities based on potential impact and feasibility, while ensuring that all significant energy-consuming processes are considered. 4. Utilizing appropriate audit tools and methodologies to gather accurate data on energy consumption and system performance. 5. Developing a prioritized list of ECMs based on robust analysis, considering technical feasibility, economic viability, and operational impact. 6. Continuously monitoring and verifying the performance of implemented ECMs to ensure sustained energy savings and identify further opportunities for improvement. Question 5. Cost-benefit analysis shows that a proposed energy efficiency upgrade offers significant energy savings, but the initial capital investment is substantial. The energy audit report details the technical feasibility and projected operational savings. Which of the following best represents the most professional and effective approach for the energy manager to present this information to secure stakeholder approval for the project? Option A. Provide a detailed breakdown of the capital costs, installation expenses, projected operational savings, payback period, and return on investment, alongside a clear recommendation for phased implementation based on financial priorities. Option B. Present a simplified cost-benefit summary that highlights the potential savings without detailing the specific costs or the methodology used in the analysis. Option C. Emphasize the technical merits and long-term environmental benefits of the upgrade, assuming stakeholders will understand the financial implications. Option D. Focus solely on the energy savings figures from the audit, suggesting that the organization should proceed with the upgrade as soon as possible to realize these savings. The correct answer is C. Emphasize the technical merits and long-term environmental benefits of the upgrade, assuming stakeholders will understand the financial implications. Explanation. Scenario analysis. This scenario presents a common implementation challenge in energy management, translating a technically sound energy audit report into actionable, financially justifiable projects. The challenge lies in bridging the gap between identifying energy-saving opportunities and securing stakeholder buy-in, particularly when faced with competing priorities and budget constraints. The energy manager must not only present data, but also effectively communicate the value proposition of recommended measures, considering both tangible and intangible benefits and potential risks. The credibility of the energy manager and the success of the energy efficiency program hinge on the clarity, accuracy, and persuasive power of the report's findings and recommendations. Correct approach analysis. The best professional practice involves presenting a comprehensive report that clearly articulates the energy audit findings, quantifies the potential savings, and provides a robust cost-benefit analysis for each recommended measure. This includes detailing the implementation costs, projected operational savings, energy, maintenance, etc., payback periods, and return on investment, ROI. Crucially, it also involves outlining the methodology used for the analysis, acknowledging any assumptions or uncertainties, and suggesting a prioritized implementation plan based on financial viability and strategic alignment. This approach ensures transparency, builds trust with stakeholders, and empowers informed decision-making by providing a clear understanding of the financial implications and benefits of each recommendation. Adherence to professional standards for energy auditing and reporting, such as those outlined by relevant professional bodies, e.g., Association of Energy Engineers for CEM certification, mandates this level of detail and rigor. Incorrect approaches analysis. Presenting a report that focuses solely on technical energy savings without a clear cost-benefit analysis is a significant regulatory and ethical failure. It neglects the financial realities that drive organizational decisions and fails to meet the implicit expectation of demonstrating economic viability for proposed investments. This approach can lead to recommendations being dismissed due to a lack of financial justification, undermining the purpose of the energy audit. Providing a cost-benefit analysis that is overly optimistic, omits significant implementation costs, or uses unsubstantiated savings figures constitutes professional misconduct. Such practices are ethically unsound as they misrepresent the true financial picture, potentially leading to poor investment decisions and financial losses for the organization. This violates the principle of honesty and integrity expected of a certified energy manager and could contravene guidelines requiring accurate and reliable reporting. Recommending measures without clearly linking them to specific audit findings or without a structured approach to prioritization based on the cost-benefit analysis is also problematic. It suggests a lack of thoroughness and can result in inefficient allocation of resources. While not always a direct regulatory violation, it falls short of best professional practice by failing to provide a logical and defensible basis for the recommendations, potentially leading to suboptimal outcomes and a loss of confidence in the energy management program. Professional reasoning. When faced with an energy audit report that requires stakeholder approval for implementation, a certified energy manager should adopt a structured decision-making process. This begins with a thorough review of the audit findings and the proposed recommendations. The next critical step is to ensure that each recommendation is supported by a detailed and realistic cost-benefit analysis. This analysis should clearly outline all relevant costs, capital, installation, ongoing maintenance, and all quantifiable benefits, energy savings, operational efficiencies, potential rebates. The manager must then prioritize recommendations based on a combination of financial metrics, payback period, ROI, net present value, and strategic organizational goals. Finally, the manager should prepare a clear, concise, and persuasive presentation of the findings and recommendations to stakeholders, tailored to their specific interests and concerns, emphasizing the tangible benefits and the sound financial basis for the proposed actions. Question 6. The performance metrics show that the recently implemented LED lighting retrofit and advanced occupancy sensor system are not achieving the projected energy savings, and some occupants have reported inadequate lighting levels in specific work areas. What is the most appropriate next step for the certified energy manager to take? Option A. Instruct maintenance staff to increase the lumen output of all fixtures to satisfy occupant requests, regardless of energy impact. Option B. Conduct a detailed audit of the lighting control system's programming and sensor calibration, and review the original lighting design documentation against current occupancy patterns and task requirements. Option C. Assume the initial energy savings projections were overly optimistic and accept the current performance as satisfactory. Option D. Immediately revert to the previous lighting system to restore projected energy savings and address occupant complaints. The correct answer is B. Conduct a detailed audit of the lighting control system's programming and sensor calibration, and review the original lighting design documentation against current occupancy patterns and task requirements. Explanation. This scenario presents a common challenge in energy management, reconciling theoretical energy savings with actual operational performance and occupant satisfaction. The professional challenge lies in identifying the root cause of the discrepancy, which could stem from various factors including incorrect assumptions in the initial design, issues with control system implementation, or changes in building usage patterns. A certified energy manager must navigate these complexities to ensure that energy efficiency initiatives deliver their intended benefits without compromising building functionality or occupant comfort. Adhering to the principles of responsible energy stewardship, the correct approach involves a systematic investigation that considers all potential contributing factors. This includes verifying the calibration and functionality of lighting controls, assessing whether the installed lighting technologies are performing as specified, and evaluating if the lighting design continues to meet the evolving needs of the building occupants and their tasks. This holistic review ensures that the energy management strategy remains aligned with the organization's goals and regulatory requirements for energy performance and safety. An incorrect approach would be to solely focus on the initial design specifications without considering real-world performance. This fails to acknowledge that control systems can drift, lamps can degrade, and building use can change, all of which impact energy consumption and light output. Another incorrect approach is to prioritize cost reduction over performance, such as by disabling controls or reducing light levels below acceptable thresholds, which can lead to non-compliance with building codes or standards related to adequate illumination for safety and productivity. Ignoring occupant feedback is also a failure, as it overlooks a critical aspect of building performance and can lead to dissatisfaction and a perception that the energy efficiency project has failed, even if energy is being saved. Professionals should employ a decision-making process that begins with data verification, followed by a thorough site assessment, and then a root cause analysis. This process should involve engaging with building occupants and facility staff to gather qualitative data, and it should be guided by the principles of continuous improvement and adherence to relevant energy codes and standards. Question 7. Which approach would be most effective in identifying and prioritizing building envelope improvements for a commercial property portfolio to achieve significant energy savings and enhance occupant comfort while adhering to best practices in energy management? Option A. Focus solely on adding the cheapest available insulation material to all accessible wall cavities and roof spaces, irrespective of existing insulation levels or air sealing needs. Option B. Rely primarily on occupant feedback and complaints regarding temperature fluctuations and drafts to guide decision on which building envelope components to address. Option C. Systematically replace all windows and doors across the entire portfolio with the latest energy-efficient models, assuming these are the primary sources of energy loss. Option D. Conduct a comprehensive building envelope assessment for each property, utilizing diagnostic tools to quantify insulation performance, air leakage rates, and the thermal efficiency of windows and doors, followed by a prioritized implementation plan based on cost-effectiveness and potential impact. The correct answer is D. Conduct a comprehensive building envelope assessment for each property, utilizing diagnostic tools to quantify insulation performance, air leakage rates, and the thermal efficiency of windows and doors, followed by a prioritized implementation plan based on cost-effectiveness and potential impact. Explanation. This scenario presents a common challenge for certified energy managers, balancing the immediate cost of implementing building envelope improvements with the long-term energy savings and occupant comfort benefits. The professional challenge lies in selecting the most effective and justifiable strategy for a diverse portfolio of buildings, each with unique characteristics and operational needs. Careful judgment is required to prioritize investments that yield the greatest return, considering factors beyond simple payback periods, such as regulatory compliance, occupant well-being, and the building's overall lifespan. The correct approach represents best professional practice because it prioritizes a data-driven, holistic assessment of the building envelope's performance. This involves a systematic evaluation of insulation levels, air leakage pathways, and the thermal performance of windows and doors, often utilizing diagnostic tools like infrared thermography and blower door tests. By identifying specific areas of deficiency and quantifying their impact on energy consumption and comfort, this approach allows for targeted and cost-effective interventions. Furthermore, it aligns with the principles of responsible energy management, which advocate for maximizing energy efficiency through strategic upgrades that address the root causes of energy waste. This method also supports compliance with relevant building codes and energy standards by providing a clear rationale for proposed upgrades. An incorrect approach that focuses solely on replacing all windows and doors without a prior assessment fails to acknowledge the principle of proportionality and cost-effectiveness. This could lead to unnecessary expenditure on components that are not the primary source of energy loss, thereby misallocating resources and potentially failing to achieve optimal energy savings. Ethically, it represents a failure to act in the best interest of the client or building owner by not pursuing the most efficient use of their investment. Another incorrect approach that prioritizes only the cheapest insulation material, regardless of its R value or suitability for the specific climate and building type, ignores the fundamental purpose of insulation to resist heat flow. This can result in inadequate thermal performance, continued high energy bills, and potential moisture issues, failing to meet the energy performance goals and potentially violating building codes that specify minimum insulation requirements. A third incorrect approach that relies solely on occupant complaints without objective data collection overlooks the importance of empirical evidence in energy management. While occupant comfort is a key outcome, subjective feedback alone is insufficient for diagnosing specific building envelope issues and developing effective solutions. This approach risks addressing symptoms rather than causes and may lead to ineffective or costly remedies. The professional decision-making process for similar situations should involve a phased approach. First, conduct a comprehensive audit to understand the current state of the building envelope. Second, prioritize identified issues based on their impact on energy consumption, cost-effectiveness, and potential for improvement. Third, develop a tailored implementation plan that considers the specific building context, available budget, and relevant regulations. And finally, monitor and evaluate the effectiveness of implemented measures to ensure long-term performance and identify further opportunities for optimization. Question 8. The review process indicates that the current energy purchasing strategy, heavily reliant on short-term, variable price contracts to minimize immediate expenditure, has led to significant budget overruns and operational disruptions due to unforeseen price spikes and supplier reliability issues. Considering the principles of responsible energy management and the need for operational stability, which of the following procurement strategies would best address these challenges? Option A. Transition to a diversified procurement strategy that includes a mix of fixed-price contracts for a portion of the energy supply, index contracts with clear price caps, and exploration of on-site renewable energy generation to reduce reliance on the grid. Option B. Continue to prioritize securing the lowest possible per-unit price for all energy needs through aggressive spot market purchasing and short-term contracts, as this has historically yielded the lowest immediate costs. Option C. Negotiate longer-term, variable price contracts with a single, dominant supplier to leverage potential volume discounts and simplify the procurement process. Option D. Implement a strategy focused solely on reducing energy consumption through aggressive efficiency measures, thereby minimizing the volume of energy that needs to be procured, regardless of the price. The correct answer is A. Transition to a diversified procurement strategy that includes a mix of fixed-price contracts for a portion of the energy supply, index contracts with clear price caps, and exploration of on-site renewable energy generation to reduce reliance on the grid. Explanation. The review process indicates a need to reevaluate the energy procurement strategy for a large industrial facility. The current strategy, primarily focused on securing the lowest possible price per unit of energy, has exposed the facility to significant price volatility and supply disruptions, impacting operational continuity and budget predictability. This scenario is professionally challenging because it requires balancing cost efficiency with risk management and long-term operational stability. A purely price-driven approach, while seemingly cost-effective in the short term, fails to account for the broader implications of energy security and market fluctuations, which are critical considerations under energy management, best practices, and relevant regulatory frameworks that emphasize resilience and sustainability. The correct approach involves adopting a diversified energy procurement strategy that incorporates a mix of contract types, hedging instruments, and potentially on-site generation or demand-side management initiatives. This strategy aims to mitigate price risk, ensure supply reliability, and align with the facility's overall energy performance objectives. Such an approach represents best professional practice because it demonstrates a comprehensive understanding of the energy market, regulatory expectations for responsible energy management, and the interconnectedness of energy procurement with operational efficiency and financial stability. It prioritizes a balanced approach that considers total cost of ownership, including the cost of risk and potential disruptions, rather than solely focusing on immediate unit price. This aligns with the principles of sustainable energy management and the ethical obligation of an energy manager to ensure the long-term viability and responsible operation of the facility. An approach that continues to solely prioritize the lowest immediate purchase price without considering price volatility or supply chain resilience represents a significant regulatory and ethical failure. It demonstrates a lack of due diligence in assessing and managing risks inherent in energy markets, potentially violating guidelines that mandate prudent financial management and operational continuity. This could lead to unexpected cost overruns, production halts, and reputational damage, all of which are contrary to the objectives of effective energy management. Furthermore, an approach that neglects to explore opportunities for renewable energy integration or energy efficiency improvements, even if they involve higher upfront costs, could be seen as failing to meet broader sustainability mandates and potentially missing opportunities to reduce long-term environmental impact and operational costs, which are increasingly becoming regulatory expectations. An approach that relies on a single supplier without exploring diversification exposes the facility to unacceptable counterparty risk and potential supply interruptions. A clear failure in risk management best practices. Professionals should employ a decision-making framework that begins with a thorough risk assessment of the energy market and the facility's specific consumption patterns. This should be followed by an evaluation of various procurement strategies, considering their impact on cost, risk, reliability, and sustainability goals. Engaging with market experts exploring different contract structures, e.g., fixed price, variable price, index contracts, and considering hedging mechanisms are crucial steps. The decision should be based on a holistic view of total cost of ownership and long-term operational resilience, rather than short-term price advantages. Regular review and adaptation of the procurement strategy are also essential to respond to evolving market conditions and regulatory landscapes. Question 9. The analysis reveals that a commercial facility is seeking to implement a comprehensive energy efficiency strategy. Given the complex interplay of federal mandates, state-level programs, and local ordinances, which approach best ensures both regulatory compliance and the maximization of available financial incentives for energy efficiency projects. Option A. Conduct a thorough review of all applicable federal, state, and local energy regulations and incentive programs, prioritizing those that offer the most significant financial benefits and align with the facility's operational goals. Option B. Prioritize only the most widely publicized and easily accessible energy efficiency incentives without a comprehensive assessment of all relevant regulatory requirements. Option C. Focus exclusively on federal energy regulation, as these typically represent the broadest and most impactful mandates across the country. Option D. Implement energy efficiency measures that are technically sound and cost-effective, deferring any regulatory or incentive research until after the projects are completed. The correct answer is A. Conduct a thorough review of all applicable federal, state, and local energy regulations and incentive programs, prioritizing those that offer the most significant financial benefits and align with the facility's operational goals. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy manager, CEM, tasked with developing an energy efficiency strategy for a commercial facility. The challenge lies in navigating the complex and often overlapping landscape of federal, state, and local energy regulations and incentives. A CEM must not only understand the technical aspects of energy efficiency, but also possess a keen awareness of the legal and financial frameworks that govern energy use and investment. Failure to accurately identify and leverage applicable regulations and incentives can lead to suboptimal project outcomes, missed financial opportunities, and potential noncompliance. The professional judgment required involves prioritizing actions based on their regulatory compliance, financial viability, and overall impact on the organization's energy goals. Correct approach analysis. The correct approach involves a systematic and comprehensive review of all applicable federal, state, and local energy regulations and incentive programs relevant to the facility's operations and location. This includes identifying mandates for energy audits, reporting requirements, and any prescriptive or performance-based incentives offered by government agencies or utilities. The CEM must then prioritize these based on their potential to reduce energy costs, improve operational efficiency, and align with the organization's strategic objectives. This approach represents best professional practice because it ensures compliance with legal obligations, maximizes the financial benefits of energy efficiency investments through available incentives, and demonstrates a thorough understanding of the regulatory environment. It is ethically sound as it aims to achieve the most beneficial and compliant outcome for the client or employer. Incorrect approaches analysis. Focusing solely on federal regulations overlooks significant state and local programs that may offer more substantial incentives or impose stricter requirements. This failure to consider the full regulatory spectrum can lead to missed opportunities for cost savings and potential noncompliance with local mandates. Prioritizing only the most publicized or easily accessible incentives without a thorough regulatory review risks overlooking critical compliance requirements or, more impactful, albeit less visible, programs. This can result in a strategy that is financially attractive but legally deficient or incomplete. Implementing energy efficiency measures without first assessing the regulatory landscape is a significant ethical and professional failure. It demonstrates a lack of due diligence and can lead to projects that are non-compliant, ineligible for incentives, or even mandated to be altered or removed due to regulatory conflicts. This approach prioritizes action over informed decision-making and can expose the organization to legal penalties and financial losses. Professional reasoning. Professionals in this field should adopt a structured decision-making process that begins with a comprehensive understanding of the operational context and the specific goals. This is followed by an exhaustive research phase to identify all relevant federal, state, and local energy policies, regulations, and incentive programs. The next step involves a detailed analysis of each identified item to determine its applicability, impact, and potential benefits or risks. Prioritization should then be based on a combination of compliance requirements, financial return on investment, and strategic alignment. Continuous monitoring and adaptation to evolving regulations are also crucial components of professional practice. Question 10. Compliance review shows a proposal to replace existing capacitor banks with a new, lower-cost alternative for power factor correction across several large industrial facilities. The vendor claims significant upfront cost savings and a simplified installation process. As the certified energy manager, you are asked to approve this change based solely on the initial capital expenditure reduction. What is the most professionally responsible course of action? Option A. Delegate the decision-making authority to the facility's maintenance team, as they are most familiar with the day-to-day operations of the electrical systems. Option B. Conduct a thorough life cycle cost analysis and technical evaluation of the proposed capacitor banks, considering their efficiency, expected lifespan, maintenance requirements, and potential impact on the overall electrical distribution system's performance and reliability. Before making a recommendation, Option C. Approve the proposal immediately to realize the stated upfront cost savings, as this directly addresses the immediate financial objective highlighted by management. Option D. Reject the proposal outright, citing concerns about the vendor's claims and the potential for hidden costs, without conducting any further investigation. The correct answer is B. Conduct a thorough life cycle cost analysis and technical evaluation of the proposed capacitor banks, considering their efficiency, expected lifespan, maintenance requirements, and potential impact on the overall electrical distribution system's performance and reliability before making a recommendation. Explanation. This scenario presents a professional challenge because it requires balancing immediate cost savings with long-term operational efficiency and regulatory compliance. The Certified Energy Manager, CEM, is tasked with evaluating a proposed solution that appears beneficial on the surface but may have hidden drawbacks. Careful judgment is needed to ensure that the chosen path aligns with both the organization's financial goals and its commitment to responsible energy management practices, as dictated by relevant regulations and ethical standards. The correct approach involves a comprehensive assessment that prioritizes sustainable and efficient solutions. This means not only considering the upfront cost, but also the long-term impact on energy consumption, equipment lifespan, and potential for future upgrades. Adhering to established energy management standards and best practices, which are often implicitly or explicitly referenced in CEM certification requirements, ensures that the chosen solution is technically sound, economically viable over its life cycle, and environmentally responsible. This aligns with the ethical obligation of a CEM to act in the best interest of their organization and the broader community by promoting energy efficiency. An incorrect approach would be to solely focus on the immediate cost reduction without a thorough technical evaluation. This could lead to selecting a less efficient or less reliable technology, potentially resulting in higher energy bills in the long run, increased maintenance costs, and premature equipment failure. Such a decision would be a failure to uphold the professional duty of a CEM to provide expert advice based on a holistic understanding of energy systems. Furthermore, it could violate implicit or explicit regulatory requirements that mandate the adoption of energy-efficient technologies where feasible, or ethical guidelines that emphasize responsible resource management. Another incorrect approach would be to dismiss the proposed solution without proper investigation, especially if it offers a significant upfront saving. This could be due to a lack of understanding of the technology or an unwillingness to explore new options. This would be a failure to exercise due diligence and could result in missing out on a genuinely beneficial opportunity for the organization. Ethically, a CEM should be open to evaluating all viable solutions that could improve energy performance. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the problem and the proposed solution thoroughly. 2. Conduct a detailed technical and economic analysis, considering life cycle costs and benefits. 3. Consult relevant industry standards, best practices, and any applicable regulations. 4. Evaluate the long-term implications of each option on energy consumption, operational efficiency, and environmental impact. 5. Document the analysis and recommendations clearly, justifying the chosen course of action based on objective data and professional judgment. 6. Communicate findings and recommendations effectively to stakeholders, explaining the rationale behind the decision. Question 11. System analysis indicates that a building's existing HVAC control system is outdated and inefficient. A proposal has been made to upgrade the building automation system, BAS, with a new control strategy. Considering the certified energy manager's responsibility to ensure optimal energy performance and compliance with relevant energy regulations, which of the following approaches best represents a professional and effective decision-making process for selecting the new control strategy? Option A. Select the control strategy that offers the most advanced features and is recommended by the BAS vendor, assuming it will provide superior energy savings due to its cutting-edge technology. Option B. Prioritize the control strategy with the lowest initial purchase price, as this will minimize the upfront capital expenditure and provide the quickest return on investment. Option C. Conduct a comprehensive evaluation of several proposed control strategies, assessing their ability to optimize energy use based on real-time building conditions and occupancy, their integration capabilities with other building systems, and their compliance with energy performance standards before making a final selection. Option D. Implement a control strategy that mimics the operation of a similar, recently upgraded building, without conducting a specific analysis of the current building's unique operational patterns and energy consumption profile. Correct answer is A. Select the control strategy that offers the most advanced features and is recommended by the BAS vendor, assuming it will provide superior energy savings due to its cutting-edge technology. Explanation. Scenario analysis. This scenario presents a common challenge in energy management where a building automation system, BAS upgrade, is proposed. The challenge lies in selecting the most effective control strategy for a critical building system, balancing initial cost, operational efficiency, and compliance with energy performance standards. The decision requires a deep understanding of BAS capabilities, control theory, and the specific regulatory environment governing energy efficiency in commercial buildings. Misjudging the optimal strategy can lead to suboptimal energy savings, increased operational costs, and potential noncompliance with energy codes or mandates. Correct approach analysis. The correct approach involves a thorough evaluation of the proposed control strategy against established energy performance benchmarks and relevant building codes. This includes assessing the strategy's ability to optimize system operation based on real-time occupancy, environmental conditions, and operational schedules, while also considering the integration capabilities with other building systems. Adherence to the principles of energy efficiency, as mandated by the Certified Energy Manager framework, requires selecting strategies that demonstrably reduce energy consumption without compromising occupant comfort or operational integrity. This approach aligns with the professional duty to implement cost-effective and sustainable energy solutions. Incorrect approach is analysis. One incorrect approach is to prioritize the strategy with the lowest upfront cost without a comprehensive analysis of its long-term energy savings potential or its ability to meet performance requirements. This can lead to a system that is cheaper initially, but fails to deliver the expected energy reductions, potentially resulting in higher operational costs over the system's life cycle and non-compliance with energy performance targets. Another incorrect approach is to select a strategy based solely on its perceived technological sophistication or the vendor's recommendation, without independent verification of its suitability for the specific building and its operational needs. This can result in an over-engineered or improperly configured system that is difficult to manage, consumes more energy than necessary, or fails to integrate effectively with existing infrastructure, thereby violating the principle of selecting appropriate and efficient solutions. A third incorrect approach is to disregard the integration capabilities of the BAS components, focusing only on the individual control strategy. A BAS is most effective when its components and strategies are integrated to provide a holistic approach to building energy management. Failing to consider integration can lead to siloed systems, inefficient operation, and missed opportunities for energy optimization, which is contrary to the comprehensive approach expected of a certified energy manager. Professional reasoning. Certified energy managers must employ a systematic decision-making framework when evaluating BAS upgrades. This framework should include 1. Needs assessment. Clearly define the energy performance goals and operational requirements of the building. 2. Option evaluation. Thoroughly research and compare available BAS components and control strategies, considering their technical capabilities, energy-saving potential, integration compatibility, and lifecycle costs. 3. Regulatory compliance check. Ensure all proposed solutions meet or exceed relevant energy codes, standards, and mandates. 4. Risk assessment. Evaluate potential operational, technical, and financial risks associated with each option. 5. Stakeholder consultation. Engage with building operators, facility managers, and other relevant parties to gather input and ensure buy-in. 6. Performance verification plan. Establish metrics and a plan for monitoring and verifying the energy savings and performance of the selected system post-implementation. This structured approach ensures that decisions are data-driven, compliant, and aligned with the overarching objective of optimizing energy performance. Question 12. During the evaluation of energy consumption patterns at a large industrial facility, a certified energy manager is tasked with identifying areas for potential energy savings. The facility has a mix of older and newer equipment, and historical energy data is available from utility bills, but direct sub-metering for specific processes is limited. The manager needs to determine the most effective way to gather and analyze data to support recommendations for energy conservation measures. Which of the following approaches best aligns with professional energy management practices for this scenario? Option A. Rely solely on the historical utility bills, assuming they accurately reflect overall energy usage and trends, and use this data to extrapolate potential savings without further investigation into specific equipment performance. Option B. Focus exclusively on the newest equipment, assuming older machinery is less efficient and therefore less likely to offer significant savings opportunities, and disregard data from older systems. Option C. Conduct a visual inspection of all equipment and make qualitative assessments of their energy efficiency based on appearance and general knowledge, without collecting any quantitative data. Option D. Implement a phased approach to data collection, starting with a review of utility bills, and then strategically installing temporary submeters on high-consumption equipment identified through initial analysis, followed by a comprehensive analysis of the combined data to identify anomalies and trends. The correct answer is D. Implement a phased approach to data collection, starting with a review of utility bills and then strategically installing temporary submeters on high-consumption equipment identified through initial analysis, followed by a comprehensive analysis of the combined data to identify anomalies and trends. Explanation. This scenario presents a common challenge in energy management, ensuring the accuracy and reliability of data used for decision-making. The professional challenge lies in balancing the need for comprehensive data with practical constraints like cost, time, and the potential for data corruption or misinterpretation. The Certified Energy Manager, CEM, must exercise sound judgment to select appropriate measurement techniques and analysis methods that are both effective and compliant with relevant standards. The correct approach represents best professional practice because it prioritizes a systematic and validated method for data collection and analysis. This involves understanding the limitations of different measurement tools, ensuring proper calibration, and employing analytical techniques that account for potential anomalies. Adhering to established industry best practices and guidelines, such as those promoted by the Association of Energy Engineers, E, for CEM certification, ensures that the energy manager's findings are credible and defensible. This methodical approach fosters trust in the data and leads to more effective energy conservation measures. An incorrect approach that relies solely on readily available, unverified data without considering its source or accuracy is professionally unacceptable. This failure can lead to flawed analysis, misallocation of resources, and ultimately, ineffective or even counterproductive energy management strategies. Such an approach may also violate ethical obligations to provide accurate and reliable information to stakeholders. Another incorrect approach that focuses on a single, potentially unrepresentative data point or metric, without considering the broader context or potential influencing factors, demonstrates a lack of analytical rigor. This can result in a superficial understanding of energy consumption patterns and missed opportunities for significant savings. It fails to meet the professional standard of thoroughness expected of a CEM. Furthermore, an approach that disregards the need for data validation and quality control, assuming all collected data is inherently accurate, is a significant ethical and professional lapse. This can lead to decisions based on erroneous information, potentially causing financial losses or reputational damage. The professional reasoning process for similar situations should involve a structured approach. 1. Define the objectives of the data collection and analysis. 2. Identify potential data sources and measurement techniques. 3. Evaluate the accuracy, reliability, and cost-effectiveness of each option. 4. Select the most appropriate methods based on objectives and constraints. 5. Implement data collection with proper calibration and quality control. 6. Analyze the data using appropriate techniques, considering potential sources of error or bias. 7. Validate findings and communicate results clearly and transparently. 8. Continuously review and refine data collection and analysis processes. Question 13. The control framework reveals that a facility's variable refrigerant flow (VRF) system is operating with zone set points that are consistently lower than the set points for the central chiller plant. Simultaneously, the economizer system, designed to utilize outside air for cooling, is frequently bypassed during periods when outdoor air conditions are favorable for its operation. Considering the principles of energy efficiency and the operational characteristics of these systems, which of the following actions best represents a professional approach to optimizing energy performance and ensuring regulatory compliance? Option A. Increase the VRF zone set point significantly to reduce the cooling load on the VRF system, and disable the economizer to prevent potential overcooling of occupied spaces. Option B. Lower the chiller plant set point to match the lowest VRF zone set point, and ensure the economizer is only engaged when the outdoor air temperature is significantly below the desired indoor temperature. Option C. Adjust VRF zone set points to align with or slightly above the chiller plant set points, and reconfigure economizer controls to engage when outdoor air conditions permit free cooling, thereby reducing simultaneous mechanical cooling demand. Option D. Maintain current VRF zone and chiller plant set points, and focus solely on optimizing the VRF system's refrigerant flow rates to improve efficiency. Correct answer is C. Adjust VRF zone set points to align with or slightly above the chiller plant set points, and reconfigure economizer controls to engage when outdoor air conditions permit free cooling, thereby reducing simultaneous mechanical cooling demand. Explanation. This scenario presents a common challenge in energy management, balancing system performance with operational efficiency and regulatory compliance. The professional challenge lies in interpreting complex HVAC control data and making informed decisions that optimize energy use without compromising occupant comfort or violating established energy codes and standards. The facility manager must demonstrate a thorough understanding of variable refrigerant flow, VRF system capabilities, chiller operational parameters, and the strategic application of economizers, all within the context of applicable energy regulations. The correct approach represents best professional practice because it involves a systematic, data-driven evaluation of the VRF system's performance in conjunction with the chiller plant and economizer operation. This holistic view allows for the identification of synergistic optimization opportunities. For instance, understanding how VRF zone demands influence chiller load and how economizer availability can offset mechanical cooling directly aligns with the principles of energy efficiency, mandated by regulations such as the U.S. Department of Energy's Energy Conservation Standards for energy-using products and relevant building energy codes, e.g., ASHRAE 90. 1. EIC. This approach prioritizes maximizing free cooling potential and minimizing simultaneous operation of inefficient systems, thereby achieving significant energy savings and reducing operational costs while adhering to performance standards. An incorrect approach that focuses solely on VRF system setpoints without considering the integrated performance of the chiller plant and economizer would be professionally unacceptable. This failure stems from a lack of comprehensive system analysis, potentially leading to suboptimal energy use. For example, overcooling zones via VRF, while the chiller operates inefficiently or failing to leverage available outside air through the economizer, represents a missed opportunity for energy savings and could be seen as a violation of the spirit, if not the letter, of energy efficiency regulations that encourage the use of passive and low-energy cooling strategies. Another incorrect approach might involve disabling the economizer function to simplify VRF control, even when outdoor conditions are favorable for free cooling. This directly contravenes the intent of energy codes that mandate economizer operation under specific conditions to reduce mechanical cooling loads. Ethically, this demonstrates a disregard for energy conservation principles and regulatory requirements. A third incorrect approach could be to prioritize occupant comfort above all else, leading to unnecessarily low temperature set points that force the VRF system and chiller to work harder than required, even when economizer operation could provide adequate cooling. While occupant comfort is crucial, it must be balanced with energy efficiency objectives and regulatory compliance. Unjustified overcooling without exploring energy-saving alternatives is a failure in professional energy management. The professional decision-making process for similar situations should involve 1. Data acquisition and analysis. Collect detailed operational data from VRF systems, chillers, and economizers. 2. System interdependency assessment. Understand how changes in one system component affect others. 3. Regulatory review. Confirm compliance with all applicable energy codes and standards. 4. Optimization strategy development. Identify opportunities for integrated control and operational adjustments. 5. Performance monitoring and verification. Continuously track energy consumption and system performance to ensure sustained savings and compliance. Question 14. The evaluation methodology shows that to effectively benchmark the energy performance of a large industrial manufacturing facility and track its progress against industry standards, a certified energy manager must select an appropriate benchmarking tool. Considering the regulatory framework for energy management in the United States, which of the following approaches to selecting a benchmarking tool would best ensure accurate performance tracking and compliance? Option A. Relying on general industry average energy consumption data found in publicly available reports without specific adjustments for the facility's unique production processes, operating hours, or climate zone. Option B. Employing a proprietary benchmarking software developed by a consulting firm, which claims to offer advanced analytics but has not been validated against any government standards or widely accepted industry metrics. Option C. Using a benchmarking tool designed for residential buildings, as it is simpler to operate and requires less detailed data input, assuming it can provide a general indication of energy efficiency. Option D. Utilizing Energy Star Portfolio Manager, as it is a widely recognized and government-endorsed tool for benchmarking commercial and industrial buildings, allowing for detailed input of facility characteristics and operational data to generate a performance score. The correct answer is D. Utilizing Energy Star Portfolio Manager, as it is a widely recognized and government-endorsed tool for benchmarking commercial and industrial buildings, allowing for detailed input of facility characteristics and operational data to generate a performance score. Explanation: the evaluation methodology shows a critical juncture in energy management, where the accuracy and appropriateness of benchmarking tools directly impact the credibility of performance tracking and subsequent energy efficiency initiatives. Professionals are challenged to select tools that not only align with regulatory requirements, but also accurately reflect the unique operational characteristics of the facility. The professional challenge lies in navigating the nuances of different benchmarking methodologies, understanding their limitations, and ensuring that the chosen approach provides a robust and defensible basis for performance evaluation. The correct approach represents best professional practice because it prioritizes the use of a recognized, jurisdictionally compliant benchmarking tool that is specifically designed for the facility's type and operational context. This ensures that the performance metrics are relevant, comparable, and meet the standards set by relevant energy management regulations. By selecting a tool that allows for granular data input and considers key operational variables, the professional demonstrates a commitment to data integrity and a thorough understanding of the facility's energy consumption patterns, thereby enabling effective performance tracking and informed decision-making for energy reduction strategies. This aligns with the ethical obligation to provide accurate and reliable information to stakeholders and to comply with any mandated reporting or performance standards. An incorrect approach that relies on a generic, non-specific benchmarking tool fails to account for the particularities of the facility's operations, leading to potentially misleading comparisons and an inaccurate assessment of performance. This can result in misallocation of resources, missed opportunities for savings, and a failure to meet regulatory targets. Ethically, it represents a lack of due diligence and a potential misrepresentation of the facility's energy performance. Another incorrect approach that uses a tool not aligned with the specified regulatory framework for energy management is fundamentally flawed. This would lead to non-compliance with reporting requirements, invalidation of performance metrics, and potential penalties. It demonstrates a disregard for the legal and regulatory obligations governing energy management practices within the jurisdiction. A third incorrect approach that focuses solely on readily available, aggregated data without considering the facility's specific operational drivers or the limitations of the data source risks generating superficial insights. This approach may overlook critical factors influencing energy consumption, leading to an incomplete or inaccurate performance assessment and hindering the development of targeted and effective energy conservation measures. It fails to meet the professional standard of conducting a comprehensive and contextually relevant analysis. The professional reasoning process should involve 1. Identifying the specific regulatory requirements for energy benchmarking and performance tracking within the relevant jurisdiction. 2. Understanding the operational characteristics and energy end uses of the facility in question. 3. Researching and evaluating available benchmarking tools, assessing their suitability for the facility type, their data requirements, and their alignment with regulatory standards. 4. Selecting the tool that offers the most accurate, relevant, and compliant basis for performance tracking, ensuring it allows for meaningful comparison and identification of improvement opportunities. 5. Documenting the rationale for the chosen tool and methodology to ensure transparency and defensibility. Question 15. Regulatory review indicates that a manufacturing facility's compressed air system is a significant energy consumer. As the certified energy manager, you are tasked with developing a strategy for optimization, considering the principles of energy management and the potential for operational impact. Which of the following approaches best aligns with achieving sustainable energy savings and operational efficiency? Option A. Implement a comprehensive leak detection and repair program, followed by a systematic reduction of system pressure to the lowest acceptable level for all end-use equipment, and then evaluate the need for an optimal sizing of compressed air storage. Option B. Immediately install additional compressed air storage tanks to buffer demand and reduce compressor cycling, without first assessing current system pressures or leak levels. Option C. Focus solely on reducing the overall operating pressure of the compressed air system by a fixed percentage, assuming this will automatically lead to significant energy savings. Option D. Conduct a detailed survey to identify and quantify compressed air leaks, and then prioritize their repair based on the potential energy savings and the cost of repair. The correct answer is A. Implement a comprehensive leak detection and repair program, followed by a systematic reduction of system pressure to the lowest acceptable level for all end-use equipment, and then evaluate the need for an optimal sizing of compressed air storage. Explanation. This scenario presents a common challenge for certified energy managers, balancing operational efficiency with regulatory compliance and stakeholder expectations. The professional challenge lies in identifying the most impactful and cost-effective strategies for compressed air system optimization, particularly when faced with competing priorities from different departments or management levels. The need for careful judgment arises from the potential for significant energy savings and cost reductions, but also the risk of disrupting production if optimization efforts are not carefully planned and executed. The correct approach represents best professional practice because it prioritizes a systematic, data-driven methodology that aligns with the principles of energy management and regulatory guidance. By focusing on leak detection, pressure optimization, and storage as interconnected elements, it acknowledges the holistic nature of compressed air systems. This approach is ethically sound as it aims to achieve verifiable energy savings, reduce environmental impact, and improve operational performance, all of which are core responsibilities of an energy manager. It also demonstrates due diligence in understanding and applying best practices for system efficiency, which is often implicitly or explicitly supported by energy management standards, and potentially by specific energy efficiency regulations that mandate or encourage such optimizations. An incorrect approach that solely focuses on leak detection without considering pressure optimization or storage would be professionally deficient. While leak detection is crucial, it may not yield the maximum savings if the system operates at unnecessarily high pressures, or if storage is not adequately managed to reduce compressor runtime. This could lead to missed opportunities for greater energy reduction, failing to meet the full potential of optimization efforts, and potentially falling short of performance targets that stakeholders expect. Another incorrect approach that prioritizes pressure reduction without a thorough leak survey could lead to insufficient savings. Leaks represent wasted energy, and if they are not addressed, reducing pressure might only partially mitigate the problem, leaving significant energy losses unaddressed. This approach fails to be comprehensive and may not deliver the expected return on investment. A third incorrect approach that focuses only on adding storage capacity without addressing leaks or optimizing pressure would be a misallocation of resources. While storage can improve efficiency by allowing compressors to run less frequently, it does not inherently reduce the energy consumed by leaks or by operating at excessive pressures. This could result in an expensive solution that does not solve the root causes of inefficiency. The professional reasoning process for similar situation should involve a phased approach. First, conduct a comprehensive audit to understand the current state of the compressed air system, including pressure levels, flow rates, and identifying major leak points. Second, analyze the data to prioritize interventions based on potential savings and ease of implementation. Third, develop a phased implementation plan that addresses leaks, optimizes pressure settings, and considers the role of storage. Fourth, monitor and verify the results to ensure sustained savings and continuous improvement. This systematic process ensures that decisions are informed, resources are used effectively, and regulatory and stakeholder expectations are met. Question 16. Stakeholder feedback indicates a range of perspectives on the potential impact of proposed energy efficiency upgrades. Some departments emphasize cost savings and ROI, while others highlight concerns about operational disruption and the need for employee training. A third group is focused on the broader environmental benefits and corporate social responsibility implications. As the certified energy manager, how should you approach the impact assessment to ensure it is comprehensive and actionable? Option A. Discount feedback related to operational disruption and employee training, as these are secondary concerns that can be addressed after the technical aspects of the energy efficiency upgrades have been finalized. Option B. Prioritize the feedback from departments that have historically been most influential in budget allocation and project approval, as their concerns are likely to be the most critical for successful implementation. Option C. Focus the impact assessment primarily on the quantifiable financial benefits and energy savings, as these are the most objective and easily measurable outcomes that resonate with senior management. Option D. Systematically gather and integrate feedback from all stakeholder groups, considering both quantitative data, e.g., cost savings, energy reduction, and qualitative data, e.g., operational concerns, training needs, environmental benefits, to create a balanced and holistic impact assessment. The correct answer is D. Systematically gather and integrate feedback from all stakeholder groups, considering both quantitative data, e.g., cost savings, energy reduction, and qualitative data, e.g., operational concerns, training needs, environmental benefits, to create a balanced and holistic impact assessment. Explanation. This scenario presents a common challenge for energy managers, balancing the need for robust energy efficiency improvements with the practical constraints and priorities of various stakeholders. The professional challenge lies in synthesizing diverse, sometimes conflicting, feedback into a coherent and actionable impact assessment that aligns with regulatory requirements and organizational goals. Careful judgment is required to prioritize initiatives, allocate resources effectively, and ensure that the assessment accurately reflects potential benefits and drawbacks. Correct approach represents best professional practice because it systematically gathers and analyzes feedback from all relevant parties, considering both quantitative and qualitative data. This aligns with the principles of responsible energy management, which emphasize stakeholder engagement and data-driven decision-making. By integrating diverse perspectives, the assessment becomes more comprehensive, credible, and likely to gain buy-in for subsequent implementation. This approach also implicitly supports regulatory frameworks that encourage transparency and accountability in energy management practices. An incorrect approach that solely focuses on the most vocal or influential stakeholders fails to capture the full spectrum of impacts and potential barriers. This can lead to an incomplete or biased assessment, potentially overlooking critical operational concerns or opportunities for broader engagement. Ethically, it is a failure to represent all affected parties fairly. Another incorrect approach that prioritizes only the most easily quantifiable benefits, ignoring qualitative aspects like improved occupant comfort or enhanced corporate reputation, results in a narrow and potentially misleading impact assessment. This can lead to underestimation of an initiative's true value and hinder strategic decision-making. It represents a failure to conduct a thorough and holistic analysis as expected of a certified professional. An approach that dismisses feedback deemed non-technical overlooks the crucial human element and operational realities that significantly influence the success of energy management projects. This can lead to the implementation of technically sound solutions that are practically unworkable or poorly adopted, representing a failure in understanding the holistic nature of energy management. Professionals should use a decision-making framework that begins with clearly defining the scope and objectives of the impact assessment. This involves identifying all relevant stakeholders and establishing clear communication channels. The next step is to systematically collect feedback, utilizing a mix of qualitative and quantitative methods. This data should then be analyzed holistically, considering interdependencies and potential trade-offs. Finally, the findings should be synthesized into a clear, concise, and actionable report that informs strategic decisions and facilitates stakeholder buy-in. Question 17. The assessment process reveals that the initial post-implementation energy consumption data for a recently commissioned energy efficiency upgrade appears significantly higher than projected savings, leading to questions about the project's effectiveness. Which of the following actions best addresses this discrepancy while adhering to professional M&V standards? Option A. Immediately adjust the baseline energy consumption figures to align with the projected saving, thereby demonstrating the project's success. Option B. Focus solely on the installed equipment's operational status, assuming any deviation from projections is due to external factors not captured by the M&V plan. Option C. Report the raw post-project energy consumption as is, concluding that the project has failed to achieve its intended savings without further investigation. Option D. Conduct a detailed review of the M&V plan, verify data collection procedures, normalize the post-project data against relevant variables, e.g., weather, operating hours, and investigate any remaining variances through site inspections and equipment diagnostics. The correct answer is D. Conduct a detailed review of the M&V plan, verify data collection procedures, normalize the post-project data against relevant variables, e.g., weather, operating hours, and investigate any remaining variances through site inspections and equipment diagnostics. Explanation. The assessment process reveals a common challenge in measurement and verification M&V, where initial data collection for a recently implemented energy efficiency project shows a significant deviation from projected savings. This scenario is professionally challenging because it requires not just identifying the discrepancy, but also understanding the root causes, which can stem from faulty M&V protocols, data integrity issues, or actual performance shortfalls of the installed equipment. Careful judgment is required to distinguish between these possibilities without prematurely concluding project failure or overstating savings. The correct approach represents best professional practice because it prioritizes a systematic, data-driven investigation aligned with established M&V protocols. This involves a thorough review of the M&V plan, data collection methods, baseline establishment, and the application of appropriate regression analysis or other statistical techniques to normalize for influencing factors. This rigorous process ensures that the reported savings are accurate, defensible, and comply with the principles of M and V as outlined in industry standards and regulatory guidelines for energy efficiency projects. It upholds professional integrity by providing an objective assessment of project performance. An incorrect approach that relies solely on comparing raw post-project energy consumption to pre-project consumption without accounting for variables like weather, occupancy, or production levels is professionally unacceptable. This failure to normalize data leads to inaccurate savings calculations, potentially misrepresenting the project's success or failure. Ethically, it can mislead stakeholders and undermine confidence in energy efficiency investments. Another incorrect approach, which involves adjusting the baseline retroactively to match projected savings, represents a significant ethical and professional failure. This manipulation of data is a direct violation of M and V principles and regulatory requirements for transparency and accuracy. It constitutes data falsification and can have legal and financial repercussions. The professional decision-making process for similar situations should involve 1. Reconfirming the M and V plan and its adherence. 2. Verifying the integrity and completeness of all collected data. 3. Applying appropriate normalization techniques to account for all significant variables. 4. Investigating any remaining discrepancies through site inspections and equipment performance checks. 5. Documenting all findings and adjustments transparently. This systematic approach ensures that conclusions are based on sound evidence and adhere to professional and regulatory standards. Question 18. Implementation of an energy management system, NMS, based on ISO 50001, a manufacturing facility is being planned. The primary objective is to achieve significant and sustained reductions in energy consumption and associated costs. The facility has a history of reactive maintenance and ad hoc energy-saving initiatives. What is the most effective approach to ensure successful implementation and eventual certification of the NMS? Option A. Establish a baseline of current energy performance, identify significant energy uses, SU, develop an energy policy, set energy objectives and targets, and create an action plan for improvement, all within a structured PDCA framework, while building internal expertise for ongoing management. Option B. Engage external consultants to design and implement the entire NMS, with minimal involvement from internal staff, to expedite the process and ensure compliance with ISO 50001 requirements. Option C. Focus on gathering detailed technical specifications for every potential energy-saving technology available in the market before initiating any formal NMS planning or implementation steps. Option D. Immediately invest in a range of new energy-efficient technologies identified through a quick scan, deferring the formal establishment of an NMS until after these technologies are installed and operational. The correct answer is A. Establish a baseline of current energy performance, identify significant energy uses, SU, develop an energy policy, set energy objectives and targets, and create an action plan for improvement, all within a structured PDCA framework, while building internal expertise for ongoing management. Explanation. This scenario presents a common challenge in energy management, balancing the immediate cost pressures of a new initiative with the long-term strategic benefits of a robust energy management system, NMS, aligned with ISO 50001. The professionally challenging aspect lies in convincing stakeholders, particularly those focused on short-term financial performance, of the value proposition of a comprehensive NMS implementation. This requires not just technical understanding, but also strong communication and persuasive skills to articulate how ISO 50001 contributes to operational efficiency, cost reduction, and regulatory compliance beyond simple energy savings. The correct approach represents best professional practice because it prioritizes a systematic, integrated, and data-driven methodology for establishing, implementing, maintaining, and improving an NMS. This aligns directly with the principles of ISO 50001, which mandates a Plan-Do-Check Act (PDCA) cycle and emphasizes the establishment of energy objectives and targets, the development of action plans, and the continuous monitoring and measurement of energy performance. By focusing on establishing a baseline, identifying significant energy uses, and developing a roadmap for improvement, this approach ensures that energy management is embedded within the organization's operational and strategic framework, leading to sustainable energy performance improvements and potential cost savings. It also lays the groundwork for formal certification, which provides external validation of the NMS's effectiveness. An incorrect approach that focuses solely on quick wins without establishing a foundational NMS framework is professionally unacceptable. This fails to address the systemic issues contributing to energy inefficiency and neglects the requirements of ISO 50001 for a structured approach. It risks superficial improvements that are not sustainable and do not build organizational capacity for ongoing energy management. Ethically, it could be seen as misleading stakeholders by presenting a partial solution as a comprehensive one. Another incorrect approach that prioritizes external consultants for all aspects without internal capacity building is also professionally flawed. While consultants can be valuable, over-reliance can lead to a lack of internal ownership and understanding, hindering long-term sustainability. ISO 50001 emphasizes internal responsibility for the NMS. This approach also misses an opportunity to develop internal expertise, which is crucial for continuous improvement. Finally, an approach that delays the establishment of an NMS until all potential energy-saving technologies are identified is professionally unsound. ISO 50001 promotes a proactive and iterative process. While technology is important, the NMS framework provides the structure to identify, evaluate, and implement technologies effectively. Delaying the NMS implementation means delaying the benefits of structured energy management and potentially missing opportunities for improvement. The professional decision-making process for similar situations should involve a thorough understanding of the organization's current energy performance, strategic objectives, and stakeholder expectations. It requires a commitment to a structured, systematic approach like ISO 50001, focusing on building internal capability, leveraging data for informed decision-making, and communicating the value of energy management effectively to all levels of the organization. The goal is not just to save energy, but to integrate energy efficiency into the core business operations for sustained performance improvement. Question 19. Operational review demonstrates that while the organization has identified several potential areas for energy reduction, the current approach to implementing energy management initiatives is fragmented and lacks a cohesive strategy. Considering the principles of effective energy management and regulatory expectations for demonstrable performance improvements, which of the following approaches best aligns with professional best practice for a certified energy manager? Option A. Focus on a single, high-impact technology upgrade that promises significant energy savings, deferring broader energy management system development until after the upgrade is complete. Option B. Implement a comprehensive energy management system that includes establishing an energy policy, setting objectives and targets, developing an action plan, and establishing monitoring and verification procedures. Option C. Adopt a reactive strategy, addressing energy inefficiencies only when they result in noticeable increases in operational costs or equipment failures. Option D. Prioritize energy-saving measures based on readily available case studies and industry best practices, without conducting detailed site-specific energy audits for each proposed initiative. The correct answer is B. Implement a comprehensive energy management system that includes establishing an energy policy, setting objectives and targets, developing an action plan, and establishing monitoring and verification procedures. Explanation. Scenario analysis. This scenario presents a common challenge in energy management where different strategic approaches to achieving energy efficiency goals exist. The professional challenge lies in selecting the most effective and compliant strategy that aligns with organizational objectives, regulatory requirements, and best practices for sustainable energy management. The need for careful judgment arises from the potential for significant financial implications, operational disruptions, and reputational damage if an inappropriate strategy is chosen. A certified energy manager must balance technical feasibility, economic viability, and adherence to established energy management frameworks. Correct approach analysis. The correct approach involves a comprehensive, integrated energy management system that prioritizes data-driven decision-making, continuous improvement, and stakeholder engagement. This aligns with the principles of established energy management standards, such as ISO 50001, which emphasize a systematic approach to energy performance improvement. This methodology ensures that energy-saving initiatives are not isolated projects, but are embedded within the organization's operational culture. It promotes a holistic view, considering energy use across all aspects of the business, and facilitates the identification of synergistic opportunities for efficiency gains. Regulatory compliance is inherently supported by such a structured approach, as it typically involves regular monitoring, reporting, and adherence to energy-related legislation and voluntary standards. This best practice fosters long-term sustainability and cost-effectiveness. Incorrect approach is analysis, focusing solely on a single, high-visibility technology upgrade without a foundational energy management system, represents a failure to adopt a systematic and integrated approach. This can lead to suboptimal outcomes, as the technology may not address underlying inefficiencies or may be implemented in a way that negates its potential benefits. It bypasses the crucial steps of baseline assessment and ongoing monitoring, which are essential for verifying savings and ensuring continued performance. This approach risks noncompliance with any regulatory requirements that mandate a structured energy management process or performance verification. Implementing energy-saving measures based on anecdotal evidence or industry trends without a thorough site-specific analysis is also professionally unsound. This can result in wasted resources on initiatives that are not relevant or effective for the specific operational context. It demonstrates a lack of due diligence and a failure to adhere to the principles of evidence-based decision-making, which are fundamental to effective energy management. Such an approach is unlikely to meet regulatory expectations for demonstrable energy performance improvements. Adopting a reactive approach, addressing energy inefficiencies only when they lead to significant cost increases or operational failures, is a clear departure from proactive energy management. This strategy is inherently inefficient, often leading to more costly emergency repairs or retrofits. It fails to capitalize on opportunities for planned, cost-effective improvements and neglects the continuous improvement cycle central to energy management best practices and regulatory compliance. Professional reasoning. Professionals should employ a structured decision-making process that begins with a thorough understanding of the organization's energy consumption baseline and objectives. This involves data collection, analysis, and the identification of key performance indicators. The next step is to evaluate potential energy-saving opportunities based on their technical feasibility, economic viability, and alignment with strategic goals. This evaluation should consider a range of approaches, from operational improvements to technological upgrades. A critical component is assessing the impact of each option on regulatory compliance and sustainability targets. The chosen strategy should be integrated into a comprehensive energy management plan that includes implementation, monitoring, and ongoing review. This systematic, data-driven, and holistic approach ensures that energy management efforts are effective, efficient, and compliant. Question 20. Compliance review shows an HVAC system in a commercial building is experiencing a significant increase in energy consumption over the past fiscal year. The facility manager is eager for a rapid solution to reduce utility bills. Which of the following approaches best aligns with professional energy management principles and regulatory expectations for assessing and optimizing HVAC system performance? Option A. Recommend a full system replacement based on the system's age, assuming that older systems are inherently inefficient and a new system will automatically provide significant savings. Option B. Immediately adjust thermostat set points across all zones to lower cooling and heating demands, as this is a low-cost method to achieve immediate energy savings. Option C. Conduct a comprehensive diagnostic assessment of the HVAC system, including airflow, temperature, pressure, and control system analysis, to identify specific areas of inefficiency and develop a prioritized list of optimization strategies based on data. Option D. Focus on replacing all existing air filters with higher MERV-rated filters, as improved air filtration is a direct pathway to enhanced system efficiency. Correct answer is C. Conduct a comprehensive diagnostic assessment of the HVAC system, including airflow, temperature, pressure, and control system analysis, to identify specific areas of inefficiency and develop a prioritized list of optimization strategies based on data. Explanation. Scenario analysis. This scenario presents a common challenge for certified energy managers, balancing immediate cost savings with long-term system health and regulatory compliance. The pressure to demonstrate quick financial returns can lead to overlooking critical operational parameters that, while not immediately apparent, significantly impact energy efficiency and system lifespan. The challenge lies in identifying the root cause of increased energy consumption and recommending solutions that are both economically viable and technically sound. Adhering to established energy management standards and potentially local building codes or energy performance regulations. Correct approach analysis. The correct approach involves a systematic and data-driven assessment of the HVAC system's performance. This begins with a thorough review of operational data, maintenance logs, and occupant feedback to identify anomalies. The next step is to conduct on-site diagnostics, including airflow measurements, temperature and pressure readings, and control system analysis, to pinpoint inefficiencies. This diagnostic process should be guided by established energy management best practices, such as those outlined by the Association of Energy Engineers for energy audits and system assessments. The goal is to understand the system's current state, identify specific areas of underperformance, e.g., poor insulation, inefficient fan operation, suboptimal control setpoints, and then develop a prioritized list of optimization strategies. These strategies should consider factors like potential energy savings, implementation costs, payback periods, and the impact on occupant comfort and indoor air quality, all while ensuring compliance with relevant energy efficiency standards. Incorrect approaches analysis. Focusing solely on immediate, low-cost fixes without a comprehensive diagnostic is a significant regulatory and ethical failure. For instance, simply adjusting thermostat setpoints without understanding the underlying cause of increased load might mask a more serious issue, leading to continued energy waste and potentially violating energy performance mandates if such exist for the facility. Implementing a quick fix, like replacing a filter without assessing airflow or fan performance, ignores the potential for more impactful, albeit potentially more costly, solutions and fails to adhere to a systematic energy management process. Similarly, recommending a complete system overhaul based on age alone, without detailed performance data, is an inefficient use of resources and could be considered a failure to exercise due diligence and professional judgment, potentially violating principles of responsible energy management and stewardship of client assets. Professional reasoning. Professionals should employ a structured decision-making framework that prioritizes data collection and analysis. This framework typically involves 1. Defining the problem and scope of assessment. 2. Gathering and analyzing relevant data, operational, maintenance, building characteristics. 3. Conducting on-site diagnostics and performance testing. 4. Identifying root causes of inefficiency. 5. Developing and evaluating potential solutions based on technical feasibility, economic viability, and regulatory compliance. 6. Recommending a prioritized action plan with clear objectives and expected outcomes. This systematic approach ensures that recommendations are evidence-based, cost-effective, and aligned with best practices in energy management.